In today's lecture, we learn about the economic dispatch, including transmission losses. Right? So when transmission distances are large, the transmission losses are a significant part of the generation and have to be considered in the generation schedule for economic operation. The mathematical formulation of economic dispatch, including transmission losses, is made our objective is minimize the f of t, where f of t is total fuel cost of generation, is equal to sigma I equal to 1 to ng fi, where ng is number of generator, such that the sigma I equal to 1 to ng pgi equal to pd plus pl, where pg is total power generation, pd is total power demand, and pl is total transmission losses of our system. According to Lagrange function, the Lagrange equal to f of t minus lambda into sigma equal to 1 to ng pg minus pd minus pl is equal to 0. Here we differentiate Lagrange function with respect to lambda and pg. So when we take differentiate equal to 0, we get the minimum value. So differentiate of Lagrange with respect to differentiate of PGI is equal to that terms contain AI plus BI PGI plus CI PGI square. So there is a PGI terms is present in that. Therefore, d Lagrange upon d PGI is equal to d of f of t upon d PGI minus lambda. PGI differentiation is 1, PD is a constant, so it is 0, and PL is changing if your generation is changing. Therefore, del PL upon del PGI is equal to 0. So, according to this, similarly, we differentiate this Lagrange function with respect to lambda, where lambda is incremental fuel cost. So, d Lagrange upon d lambda is equal to sigma I equal to 1 to ng. This term is 0. So, sigma I equal to 1 to ng PGI minus PD minus PL. If you subtract, here it is minus. If you remove the cons at the time, sigma I equal to 1 to ng PGI minus PD plus PL equal to 0, which is our equality constraint. So, as per the economic operation, the incremental fuel cost of all the generator will be the same. So, del Ft upon del Pgi equal to del Fi upon del Pgi. So, we get this coordination equation if we consider the transmission losses, which is dFi upon dPgi plus lambda dPl upon dPgi equal to lambda, right? If you subtract this, right, so you will get this equation. If you take main as lambda, so you will get dFi upon dPgi equal into 1 upon 1 minus del PL upon del PGI. It is not whole. It is 1 minus del PL upon del PGI. Right? Where 1 upon 1 minus del PL upon del PGI is equal to penalty factor, which is denoted by Li. So the coordination equation, including the transmission losses, are given by lambda equal to dFi upon dPGI into Li. And Li is your penalty factor. The equation states that the minimum operation cost is obtained when the product of the incremental fuel cost and the penalty factor of all units is same when losses are considered. A reserve general expression for the loss PL is given by PL equal to sigma m into sigma n PGM plus BMN plus PGN. Where M is your one bus, N is your second bus. So losses in between these two buses is calculated using this generalized equation. Where B is your BMN, BNO, and B00 is your loss coefficient. It depends on load composition. The assumption here is that the load varies linearly between maximum and minimum value. As a simple expression of above expression is PL equal to sigma n, PGM, BMN, PGN. An average set of loss coefficient may be used over the complete daily cycle in the coordination of incremental production cost and incremental transmission losses. In general, BMN equal to BNMN can be expanded for a two-plant system as PL equal to B11 PG1 plus 2B12 PG1 PG2 plus B22 PG2 square. Here M is your 1 and N is your 2. So according to that, you will get this equation. Now we solve some example based on this method. A generator is supplying a load. An incremental change in the load of An incremental change in load of 4 MW requires generators to be increased by 6 MW. The incremental cost at the plant bus is rupees 30 per megawatt hour. What is the incremental cost at the receiving end? So here lambda is initially given is plant 1 is 30 rupees. So here two bus systems are there. One generator is present on this bus and one load is present on second bus. The change in load means del PD is equal to 4 megawatt increased by change 6 megawatt. Change in generation. So del PG is 6 megawatt. So your losses is 6 minus 4 means del PL is 2 megawatt. So del PL equal to del PG minus del PD equal to 2 megawatt. So according to the coordination equation including the transmission losses, lambda equal to dF1 by dPg1 into 1 upon 1 minus del PL upon del PG. Here dF1 by dPg1 is equal to 30 rupees per megawatt hour. Del PL 2 megawatt, del PG 6 megawatt. So you will get lambda equal to 45 rupees per megawatt hour at the receiving end. Now second example. In a system with two plants, the incremental fuel costs are given by del F1 by del Pg1 equal to 0.01 Pg1 plus 20 rupees per megawatt hour. Second cost function is dF2 by dPg2 equal to 0.015 Pg2 plus 22.5 rupees per megawatt hour. The system is running under optimal schedule with Pg1 and equal to Pg2 equal to 100 megawatt. If del PL upon del Pg2 equal to 0.2, find the plant penalty factors and del PL upon del Pg1. So here the plant penalty factor of generator 2 is del PL upon del Pg2 equal to 0.2. So according to the equation of penalty factor, Li equal to 1 upon 1 minus del PL upon del Pg1. Right? So this is our coordination equation including the transmission losses, and this is our penalty factor equation. Li equal to 1 upon 1 minus del PL upon del PGI. So here del PL upon del Pg2 is already given to you, right? So it is 0.2. The cost function for plant 2 is 0.015 Pg2 plus 22.5. Initially the Pg1 equal to Pg2 equal to 100 megawatt. So put the value of Pg2 in this equation. In this equation, you will get 0.015 into 100 plus 22.5, 1 upon 1 minus del PL upon del Pg2, which is 0.2 equal to lambda. So you will get the value of incremental fuel cost is 30 rupees per megawatt hour. So plant penalty factor of generator 2 is 1 upon 1 minus 0.2 equal to 1.25. Similarly, the coordination equation for plant 1 is del F1 by del Pg1 into L1 equal to lambda. So del F1 by del Pg1 it is given by 0.01 into Pg1 plus 20 into L1. Now Pg1 is 100, right? So 0.01 into 100 plus 20 into L1 equal to 30. So you will get L1 equal to 1.48, right? What is 30? It is incremental fuel cost, right? So L1 equal to 1 upon 1 minus del P upon del PG. Put the value of L1 1.428. You will get del PL upon del PG1 equal to 0.3. Now another example. A two-bus system is shown in figure. If 100 megawatt is transmitted from plant 1 to the load, a loss of 10 megawatt is incurred. The system's incremental cost is rupees 30 per megawatt hour. Find PG1, PG2 and power received by load if dF1 by dPG1 equal to 0.02 PG1 plus 16 rupees per megawatt hour, dF2 by dPG2 equal to 0.04 PG2 plus 20 rupees per megawatt hour. Now, first of all, understand this example. If you transmit 100 megawatt from this generator to the load, a loss of 10 megawatt is incurred, right? Since the load is connected at bus 2, now losses is incurred when plant 2, this generator is supplying to this load, right? Okay, because load is connected at this bus. If this generator is supplying, then at that time, now losses will be incurred. Therefore, according to the loss formula, B12 equal to 0 and B22 equal to 0. There is no loss coefficient of generator 2, right? So our loss formula is become PL equal to B11 PG1 square. So if 100 megawatt transmitted from plant 1, loss is 10 megawatt is incurred. So PG1 equal to, right, 100 megawatt and PL equal to 10 megawatt, you will get the loss coefficient equal to 0.001 megawatt inverse. So if you differentiate this equation with respect to Pg1, you will get del PL upon del Pg1 equal to 2B11 Pg1, right? And del PL upon del Pg2, there is no Pg2 terms is present, therefore it is equal to 0. So according to coordination equation, dFi upon del Pgi plus lambda del PL upon del Pgi equal to lambda. So for plant 1, it is del F1 by del Pg1 plus lambda del PL upon del Pg1 equal to lambda. Put the value of del PL upon del F1 by del Pg1 lambda in this equation, right? You will get this type of equation 0.02 Pg1 plus 16 plus lambda is 30 plus 30 into 2 into 0.01 into Pg1 equal to 30. So you will get Pg1 equal to 175 megawatt. Similarly for plant 2, dF2 by dPg2, Pg2, here there is a mistake, dF2 by dPg2 plus lambda dLPL upon del Pg2 equal to lambda. So del PL upon del Pg2, it is already 0. So put the value of dF2 by dPg1, Pg2, which is 0.04 Pg2 plus 20 equal to 30. So you will get the value of Pg2, which is 250 megawatt. So losses B11 Pg1 square, right? This equation. Okay, we use this equation for finding the new losses because now our generator is Pg1 is changed. Initially it is 100 megawatt, then at that time 10 megawatt losses. Now our generator is 175 megawatt. So new losses. So B losses equal to B11 Pg1 square is equal to 0.001 into new generation is 175 megawatt. So 175 square, you will get new losses 30.625 megawatt. So total demand is equal to Pg1 plus Pg2 minus losses. So Pg1 is 175, Pg2 is 250 and losses is 30.625. So you will get new generation total demand. So you will get total demand is equal to 394.375 megawatt. Thank you.